All right, time for everybody's favorite topic, which is significant figures. Hopefully, you nailed these in Chem 50, and this all seems review. What we're doing is that we are going to be looking at calculations involving numbers, and they're no longer going to tell you round to two decimal places, round to the nearest tenth. Instead, it is expected that you are going to maintain precision of data by keeping the significant figures or the precision of your measurements. So the first thing we have to talk about is, what do we mean by significant figures? Significant figures is counting the number of digits in a number that are significant. Now, the easiest way I think of this is that if you were to write a number in scientific notation, would you include that number or no? So the first rule is that anything that's not a zero is obviously significant. So if you had a number like 3,456, every number in that measurement is significant. So this would have four significant figures. If you had a number like 2.7945 times 10 to the 6th, the times 10 to the 6th is what makes it scientific notation. So obviously you would add 6, or you'd move the decimal place to the right 6 places, so you'd add 2 zeros. But the 27945 are all significant, so 5. Then we get to the conversation around zeros. Leading zeros are zeros that precede all non-zero digits, right? So if you look at this diagram above, it's the blue squared numbers. They are your leading zeros. And if you were to write a number in scientific notation like 0.0048, you would write it as 4.8 times 10 to the negative 3. You would never write the preceding zeros, okay? And so they don't count. So this number here only has 2 significant figures. This one has 1. This one has 1, 2, 3, 4. Done. The next conversation on zeros is captive zeros. Captive zeros are things that are inside of non-zero integers, and without them, the number wouldn't be what the number was. So for example, 2.008 times 10 to the negative 3, if I took out these two middle zeros, it would be 2.8, which would be a very different number with very different precision. So this one has 4 sig figs. 10,001 has 5 sig figs. 6.0145 times 10 to the 1, 5 sig figs. 1, 2, 3, 4, 5. Cool. And then the last thing for zeros is trailing zeros, and this is where the number, or where it gets kind of complicated. Trailing zeros are only significant if the number contains a decimal point. So for example, if you had 9.300, these zeros are significant. This shows that my instrument was reading with an accuracy, or not an accuracy, sorry, a precision of 3 decimal places. My last known line would be a second decimal place, and I'd be estimating the third. So this is 4 sig figs. Whereas a number like 150, if I said, yeah, I made about 150 bucks, well, maybe I made $150.62. Maybe I made $151, but I made about 150. It is not known whether this zero is precise or not. So 150 is 2 sig figs, and I could write it in scientific notation as 1.5 times 10 to the 2. That would also be 2 sig figs, and it would be a bit more obvious. If I wanted to make that zero significant, I would have to put a decimal point. So 150 decimal shows that this zero was significant, and all of a sudden that trailing zero would count, and there would be 3 sig figs. Same thing as if I put 1.50 times 10 to the 2. Because I wrote it in the scientific notation, I am saying that it is significant. And then there's these crazy numbers like 1 decimal 640000. Because it contains a decimal place, that is showing that this is a really precise instrument, and this would have 8 sig figs. If that decimal place didn't exist, and this was 16,400,000, then those zeros would not count, and there would be 3 sig figs. And then the last rule is that if you have exact numbers, so things where there is no chance of having a decimal on there, it's as precise as it can get, that we count it as an unlimited number of sig figs. So for example, if I said there's 5 people in this room, Well, I'm not going to say there's 5.2 people. You can't have 0.2 of a person. So that would be an unlimited number of sig figs. Same with a number like pi. Pi is an irrational number that goes forever, and so it's unlimited, as well as proportions. So if I say that 1 inch is equivalent to 2.54 centimeters, that is an exact measurement, right? 1 inch is 2.54 centimeters, so that would also be an unlimited sig figs. There are some proportions where the comparison would be rounded, and then you'd have to count it. But we will just say that if you're ever using a conversion or something along these lines, just don't count the conversion into your sig figs. Go based on the number that you started with. Awesome. So simple. Take these 6 questions, pause your video, and determine how many sig figs each of these has. Go. All right, here's the correct answers. 3, 3, 4, 2, 5, and 2. If you got any of those wrong, look back at the rules and see if you can figure out why, or come and ask me a question.